Thank you for your introduction. My name is Taiga Hiroka. In this talk, I talk about certified everlasting zero knowledge proof for QMA. This work is joint work with Tomoyuki Morimae, Ryo Nishimaki, and Takashi Yamakawa. First, let me explain QMA briefly. Roughly speaking, QMA is a quantum version of NP. In this class, the quantum polynomial time verifier can check whether the instance X is yes instance or not. First, the verifier receives a quantum witness psi from the prover, and he checks whether the instance X is yes instance or not. When the instance X is yes instance, there exists a quantum witness psi such that the verifier accepts with high probability. On the other hand, when the instance X is not yes instance, for all quantum states psi, the verifier rejects with high probability. If the language L satisfies these properties at the same time, we say that the language L is in QMA. In this talk, I'll consider zero knowledge proof for QMA. In the zero knowledge proof for QMA, a quantum polynomial time prover with a quantum witness psi can convince a verifier that the instance X is yes instance without revealing any information beyond the fact that the instance X is yes instance. Broadbent and Grillo have constructed zero knowledge proof for QMA from classical commitment with statistical binding and computational hiding. The outline of their construction is as follows. First, the prover randomly generates n-length classical bit strings and then commits them using classical commitment with statistical binding and computational hiding. Then the verifier randomly generates I and sends it to the prover as a challenge. Then the prover sends the ith bit of A to the verifier. The verifier checks whether the instance X is yes instance or not. Their construction satisfies following three properties. The first property is completeness. This guarantees that when the instance X is yes instance, the verifier accepts with high probability. The second property is statistical soundness. This guarantees that when the instance X is not yes instance, the verifier rejects with high probability for any unbounded malicious prover that tries to make the verifier accept. The third property is computational zero knowledge. This guarantees that no quantum polynomial time malicious verifier learns anything beyond the fact that the instance X is yes instance. Now, I will explain our motivation. Although zero knowledge proof for QMA satisfies these properties, computational zero knowledge has a risk. In fact, new efficient algorithms or improvements of computers may solve the problem underlying the security of computational zero knowledge. So computational zero knowledge does not necessarily imply a long-term security. In other words, in computational zero knowledge, malicious verifier may obtain information beyond the fact that the instance X is yes instance. So this is undesirable. One way to resolve the problem is to use zero knowledge proof for QMA with statistical zero knowledge. In a protocol with statistical zero knowledge, the security holds against unbounded malicious verifier. So the security will never break in the future. However, it is believed that we cannot construct zero knowledge proof for QMA with statistical soundness and statistical zero knowledge at the same time. So if the protocol satisfies statistical soundness, zero knowledge property must be computational one. And thus the malicious verifier can obtain information beyond the fact that the instance X is yes instance. So our question is as follows. Can we construct zero knowledge proof for QMA where the zero-knowledge property holds in a long term without compromising statistical soundness. In our work, we resolve this question affirmatively. For that, first, we introduce a new notion of zero-knowledge property, which we call certified everlasting zero-knowledge, and then construct zero-knowledge proof for QMA with statistical soundness and certified everlasting zero-knowledge. Now, I will explain an intuitive definition of certified everlasting zero-knowledge. In a protocol with certified everlasting zero-knowledge, a malicious verifier can issue a certificate which shows that he deletes the information received from the prover. The prover can check whether the certificate is valid or not using her internal information. When the certificate is valid, the prover accepts the verifier, and otherwise rejects the verifier. When the prover accepts the verifier, even if its computing power becomes unbounded after that, he cannot obtain information beyond the fact that the instance X is yes instance. This is an intuitive definition, certified everlasting zero knowledge. So in the certified everlasting zero knowledge, the security will never break in the future when the certificate is valid. Note that certified everlasting zero knowledge does not guarantee any security when the certificate is not valid. However, the prover can prevent the verifier from refusing to output a valid certificate. So we believe that this security is still meaningful. Now, I will explain our construction. For that, I will explain why the known construction is not secure against unbounded malicious verifier. In the known construction of zero knowledge proof for QMA, the classical commitment satisfies only computational hiding. So malicious unbounded verifier can obtain the committed value from the classical commitment. This fact breaks zero knowledge property of the known construction. To resolve the problem, we introduce a new quantum commitment with a new hiding property, which we call certified everlasting hiding. In this hiding, a malicious receiver can issue a certificate, which shows that he deletes the quantum commitment. When the certificate is valid, even if receiver's computing power becomes unbounded after that, he cannot obtain the committed value. In our work, we have constructed a quantum commitment with statistical binding and certified everlasting hiding from an ordinary classical commitment with statistical binding and computational hiding in the quantum random oracle model. Now, I will explain an informal construction. Note that this is not a formal construction for ease of understanding. So if you are interested in our formal construction, please see our paper. First, in our construction, the sender randomly generates two classical bit strings and keeps one as a secret key and the other as a verification key. Then the sender generates BB84 states according to these classical bit strings. The basis of these quantum states depends on the secret key. If the secret key is equal to 0, the sender generates computational basis states. On the other hand, if the secret key is equal to 1, the sender generates Adamant basis states. And the bit values of these quantum states is equal to the verification key. Then the sender encrypts message M using the bit values of computational basis state as follows, where H is a hash function. Then the sender encrypts the secret key using classical commitment with statistical binding and computational hiding. Then the sender sends them to the receiver as a commitment of the message M. Our construction satisfies correctness. This guarantees that when the protocol is executed honestly, the receiver can recover the message M correctly. When the receiver wants to recover the message M, the receiver requests the sender to send the secret key. And the receiver checks whether the secret key is equal to the committed value or not. Now the sender behaves honestly, so the receiver accepts with an overwhelming probability. Remind that the secret key is the base of these quantum states. So by measuring computational basis states in the computational basis, he can obtain 0, 1, and by computing its hash function, he can recover message M. And our construction satisfies statistical binding. This statistical binding intuitively guarantees that no unbounded malicious sender can change the probability distribution that the receiver obtains message M. Now, I will explain an intuitive reason why our construction satisfies the statistical binding. And the malicious sender tries to make the receiver accept the different secret key other than the sender first committed. However, even unbound malicious sender cannot make the receiver accept the different secret key, since the classical commitment satisfies statistical binding. This fact implies that the secret key used to extract message M from this part is determined only by the commitment that the sender first sent. So even unbound malicious sender cannot change the probability distribution that the receiver obtains message M after she sends the quantum commitment. And our construction also satisfies certified everlasting hiding. In this hiding, malicious receiver can issue a certificate which shows that he deletes the quantum commitment. When the certificate is valid, even if its computing power becomes unbounded after that, he cannot obtain the committed value. When the sender wants to delete the quantum commitment, the sender requests the receiver to measure all these quantum states in the normal basis and receive the measurement outcomes as a certificate. Then the sender checks whether the certificate is equal to the verification key, where the secret key is equal to 1. If so, the sender accepts the receiver, and otherwise rejects the receiver. When the sender accepts the receiver, even if its computing power becomes unbounded after that, and the secret key is leaked from the sender, he cannot obtain information of message M correctly. Intuitively, this is what certified everlasting hiding guarantees. Now, I will explain an intuitive reason why our construction satisfies certified everlasting hiding. And when the receiver's computing power is limited, he cannot obtain the basis of these quantum states from the commitments. This is because the classical commitment satisfies computational hiding. So in order to make the sender accept with high probability, he has to measure all these quantum states in the normal basis and send the measurement outcomes as a certificate. On the other hand, if he measures the computational basis states in the normal basis, these quantum states collapses to random classical bit string, and he can no longer obtain the bit values of computational basis states, even if its computing power becomes unbounded, and he obtains the basis of these quantum states. This is the intuitive reason why our construction satisfies certified everlasting hiding. Once we have constructed quantum commitments with these properties, we can construct zero knowledge proof for QMA with certified everlasting zero knowledge and statistical soundness at the same time by combining this quantum commitment with zero knowledge proof for QMA of Broadbent and Grillo. The outline of our construction is as follows. First, the prover randomly generates in length classical bit string and commits them using our quantum commitment. Then the verifier randomly generates I and generate the certificate of the quantum commitment. Other than this, I. Then the verifier sends them to the prover. The prover checks whether all certificates are valid or not using her internal information. Then the prover sends the ith bit of A to the verifier. The verifier checks whether the instance X is yes instance or not. Our construction satisfies these properties from the zero-knowledge proof for QMA of Broadbent and Grillo. And our construction also satisfies certified everlasting zero-knowledge, which is main target of our work. Now, I will explain an intuitive reason why our construction satisfies certified everlasting zero-knowledge. When the certificates issued by the verifier are valid, he cannot obtain the committed value from the information received from the prover. So he cannot obtain these ones. So he cannot obtain information beyond the fact that the instance X is instance. In our work, we have constructed the knowledge proof for QMA with these properties by using quantum mechanics. Note that quantum mechanics is essential for our construction. Finally, I will explain the reason why the quantum mechanics is essential for our construction in the next slide. In the classical world, certified everlasting zero knowledge implies statistical zero knowledge. So in the classical world, we cannot construct certified everlasting zero knowledge proof for QMA or NP. To explain that, we will consider the zero knowledge protocol between the classical prover and the classical verifier. So the messages between them are also classical. So the malicious verifier can copy the information received from the prover, since these are classical bit strings. And by using the copied information, the malicious verifier can issue a valid certificate. From the definition of certified everlasting zero knowledge, when the certificate is valid, his computing power becomes unbounded. So he can access to P1, P2 received from the prover. So P1, P2 must be secure against unbounded verifier at the point that he receives them. So in the classical world, certified everlasting zero knowledge implies statistical zero knowledge. On the other hand, in the quantum world, the same discussion does not go through. This is because in the quantum world, even malicious verifier cannot copy the information received from the prover, since the quantum no cloning theorem holds in a quantum world. So in the quantum world, certified everlasting zero knowledge does not necessarily imply statistical zero knowledge. Now, I summarize this talk. First, in our work, we have introduced a new notion of quantum commitment with statistical soundness and certified everlasting hiding, and have constructed. Second, we have introduced a new notion of zero knowledge property, which we call certified everlasting zero knowledge, and have constructed certified everlasting zero knowledge proof for QMA. Open problems are as follows. The first open problem is that, can we construct other cryptographic primitives with certified everlasting security? Note that a recent follow-up research shows that we can construct a protocol with certified everlasting security for public encryption, fully homomorphic encryption, and so on in this work. And our recent work shows that we can construct functional encryption with certified everlasting security for all NC1 circuits, but the number of key query is a priori bounded. It is open problem whether we can construct other cryptographic primitives. The second question is, can we define a different type of everlasting security and construct a protocol with the security? In our work, we have defined certified everlasting security, where computational assumptions are needed only before the valid certificate is issued On the other hand, we may be able to define other type of everlasting security where computational assumptions are needed only temporarily, but it remains open. Now I finish my talk. Thank you for your listening.
Okay. Yeah. Thanks a lot for the talk. Thanks a lot for the talk. I have a question about the solution to
Yeah.
So you described the two functions.
Yeah.
And essentially now to doing enforcing the certified deletion along the method and then comment. And I wonder whether
our formal
Please repeat the question.
First, we use one-time secret encryption with certified deletion by Broadband Islam and the commitment with these properties and the quantum random molecule. Okay.
So my question was
Please repeat the question.
Sorry, it's difficult. So your question is about statistical soundness. So, statistical binding. Yeah. Okay. Yeah, the sender can, of course, the sender can change these quantum states, but the sender cannot change the secret key. So after she sends these quantum states, she cannot change these quantum states, So even unbounded malicious sender cannot change the probability distribution. Okay. But the message is only from the sender to the receiver. So even unbounded malicious sender cannot change the quantum state after she sends the quantum state, I think. Communication must be quantum. Yeah. But it is impossible because he can copy the classified bit strings from the prover, so we cannot construct certified everlasting zero knowledge proof for QMA in the classical communications. Sure.
Let me get that for you. Okay, and yours is this one?
Yes.
Excellent.
Actually hearing.
So where's the slideshow? How do I get to the slideshow? Like hidden by the Zoom. Now I need to force you.
It was this one. Is it this one? Yeah. Thanks for the introduction. I'm Takashi from NTT and Kyoto University, and I'm talking about quantum commitment and signature without one-way functions. And this is a joint work with Tomoyuki Morimaya from Kyoto University. So as you all know, the one-way functions are a fundamental building block in cryptography. And in the classical cryptography, one function is known to be the minimum assumption for any non-trivial cryptography, including symmetric encryption with short keys, public encryption, key exchange, digital signatures, commitment, and so on. And next, I will talk about quantum cryptography. So quantum information is awesome. And one of the most surprising implications of quantum information for cryptography is quantum key distribution. So this is an information theoretically secure key exchange protocol by using quantum communication. And as I said, so in the classical cryptography, key exchange protocol has to at least assume the existence of one function. So this changes the landscape of cryptography when we consider quantum communication. And after the invention of quantum key distribution, people started to expect that other cryptographic primitives can also be realized by using quantum communication in an information theoretically secure way. However, it turned out that actually many cryptographic primitives are impossible to achieve information theoretical security, even with quantum communication. And those primitives include symmetric public encryption, digital signatures, commitment, and so on. So, but if the information theoretical security is impossible, then the next natural question is what is the minimum assumption needed for constructing them? And especially our main question is one function necessary for constructing them when using quantum communication. And this is our result. We showed that one-way functions are actually not needed for constructing commitments and one-time signatures using quantum communication. And
recent results show that commitment scheme actually implies oblivious transfer and multi-party computation in the quantum setting. So this also means that one-way functions are not needed for constructing a general multi-party computation protocol in the quantum setting. And for proving this, what we actually do is to construct these primitives from what is called pseudo-random quantum states. I will explain about this later, but the point is that there's evidence that pseudo-random states does not imply the existence of one function or even BQP not equal to QMA. And by combining them, we actually prove this takeover message. So one-way functions are not the minimal assumption for quantum crypto. And this is the brief overview of our result. And from now, I will explain a little bit more detail about the result. So first, let me explain what is pseudo-random quantum states. And this is roughly a quantum analog of pseudo-random generators. So this is an algorithm that, this is an algorithm that takes classical string K as input and outputs quantum state psi K. And as security notion, we require computational indistinguishability like this. So this says that for any polynomial T, T copies of psi K for randomly chosen key K is computationally indistinguishable from T copies of power random state phi. So where power random is just intuitively a uniformly random quantum state. And by default, we require this for unbounded polynomial T, but we also consider a weaker type of security where T is limited to 1, in which case we call it 1 PRS. And here I remark that for 1 PRS, this is non-trivial only when G is length increasing. But for unbounded polynomial T, PRS is non-trivial even for length decreasing one. And here are several known results about PRS. And G et al. Proved that one-way functions, so they constructed pseudo-random state based on one-way functions, but they left the other direction open. And the recent work by Gretschmer proved that there is a quantum oracle relative to which BQP equals QMA, but PRS exists. So this means that it is unlikely that PRS implies one function, and in the sense that this is impossible relative to quantum oracle. So, okay, so as I said, so PRS doesn't seem to imply one function. So our goal is to construct commitment digital signatures from pseudo-random state. And so first I will explain commitment. The commitment is a protocol between sender and receiver, where sender has a message B, which is a bit now. And in the commit, we have two phases called commit phase and a review phase. In the commit phase, the sender generates some commitment com B depending on the message B and sends it to the receiver. And the review phase, the sender sends B along with some review information, rev B, and then receiver verifies it and accepts or rejects. And we require two security notions for commitment. The first is hiding, which means that commitment hides B. And we especially consider computational hiding, which means that commitment to 0 and commitment to 1 are computationally indistinguishable. And the second is binding. And binding intuitively means that the sender cannot change his mind after sending com B. However, we have to be careful about when defining binding property for quantum commitment, because in the quantum case, especially when the commitment is quantum, the naive notion of binding is impossible because the malicious sender may generate a superposition of commitment to 0 and commitment to 1, in which case the commitment can be open to 0 and 1 with probability 1/2 for each. And so when considering quantum commitment, so we have to consider a little bit relaxed notion of binding, which is often called some binding property. So this means the following. Let PB be the probability that the sender can open the commitment to B, then the sum of probability P0 and P1 should be almost equal to 1, except for the negligible difference. And this is our construction of commitments from one PRS. Here, one PRS records that one PRS means that when one is only given one copy of PRS state, PRS, so you cannot distinguish it from how random. And so we assume one PRS from n bit to 3n qubit. And then the protocol works as follows. So in the commit phase, the sender generates a state over two registers, R and C, where R stands for the review register and C stands for commit register. And if we, in the commit phase, it only sends C register, and in the review phase, it also sends the review register along with the committed bit B. And in the commit phase, it only sends the C register. So let's look at C register tracing out the R register. Then when B equals 0, then this is simply pseudo-random state psi k for randomly chosen k. On the other hand, for B equal 1, this is pseudo-random state psi k quantum parted with random key x and z. And yeah, this is a commitment protocol which we construct, and this is a very simple protocol. So we have to prove that this satisfies hiding and binding, and especially computational hiding and statistical binding. And for hiding, so what we have to prove is that psi k and its quantum parted state is computationally indistinguishable. For proving this, we first consider our random state phi and its quantum parted state. And because both states look maximally mixed states, so we can show that they are statistically indistinguishable. And also, by the security of one PRS, psi k for randomly chosen k is computationally indistinguishable from how random state phi. Therefore, by combining them, we can conclude the computational hiding property of the commitment protocol. And next, for the binding, so by using known result by Yan, it actually suffices to prove that the fidelity between commitment to 0 and commitment to 1 are negligible, which means that commitment to 0 and commitment to 1 information theoretically fall apart. And I will not explain the actual proof for this, but the intuition is as follows. So for commitment to 1 is a maximally mixed state in 2 to the 3n dimensional space, because this is a one-time parted state of something. On the other hand, the commitment there is just a mix of 2 to the n states, of which are pseudo-random states, because the possible number of quantum states is 2 to the n, because there are this many keys for the PRS. Therefore, the mix of 2 to the n states cannot be information theoretically close to maximum mixed state in the 2 to the 3n dimensional space. So they should be information theoretically far apart. And this is intuition of the proof of binding. And yeah, so now we get commitments from one PRS. And as I already mentioned, recent result from Bautfeld et al. Shows that commitment implies obvious transfer and also multi-party quantum computation by using quantum communication. And actually, we cannot simply combine our result and theirs because the Bautfeld et al. Assumed classical commitments, whereas we constructed quantum commitments. However, we observed that we can use quantum commitment in their construction of MPQC by using a technique developed by another work by Fan et al. And where they gave a general technique to replace classical commitment with quantum one. So by using this technique, we can actually use our quantum commitment in the construction of MPQC by Bautfeld et al. And then so we obtain one MPQC from one PRS. And as a result, we can say that MPQC may not need one-way functions. And next, I will move on to one-time signatures. So one-time signature is a protocol between signer and verifier, where signer holds signing key, SK, and verifier holds verification key, VK. And signer also has a message M to sign. And to sign to the message M, the signer generates the signature sigma M by using his secret key escape or signing key escape, and then send the signature sigma M to the verifier along with the message. And then verifier verifies if it is valid signature or not and accept or reject. And one-time security means that given verification key and the sigma M, which is the signature for message M, one cannot find the signature for M prime, which is different from M. And this is a one-time signature. And here let me recall classical, very simple construction of one-time signature, which is called Lamport Signature. And especially I focus on single bit message case. And then the construction is very simple. So F is a one-way function. And the signing key is a pair of inputs, x0 and x1. And the verification key is a pair of f of x0 and f of x1. Then to sign to a message, one-bit message M, the signature is just either of x0 or x1, depending on the message. And then the verifier verifies it in an obvious manner. And then the one-time security is clear from 1 minute of F. So basically, imagine that we are given f of x0 and f of x1, and given either x0 and x1, and we are required to find the other image, which is impossible by the 1 minute of one function. And our construction of one-time signature from PRS is very similar to Lamport signature. And the only difference is that we use PRS instead of one-way function. So we assume PRSG, which maps a classical string K, classical key K to some quantum state psi K, and we simply use this G instead of one-way function F in the Lamport signature. And then in the Lamport signature, we have to assume that F is a one-way function. So as an analogy, we have to assume some kind of one-way property for pseudo-random state. And what we need for security proof is the following one-wayness property of G. So when we are given psi, the T copies of psi K for randomly chosen K, it is hard to find K prime such that psi K prime is close to psi K. The probability of finding such K prime is negligible. And this is the one-wayness property. And we prove that if we assume that G is a length increasing pseudo-random state, then it is also one way. And this is a natural analog of classical statement, which says PRG, length increasing PRG is automatically one way. And so this is just a natural analogy in the quantum setting. And so once we obtain the one-wayness, then this suffices for proving one-time security of this signature scheme. And here are several remarks about our one-time signatures. And first, I remarked that the verification key of our protocol is content. And this is not very useful in practice, but let me remark that this is actually needed for PRS-based construction, because otherwise, if VK is classical, then we can break the protocol by using QMA oracle, where we consider the valid signature as a witness. Therefore, but for constructing the quantum signature from PRS, we have to assume that VK is content, at least in the relativized world. And the next remark is that the scheme is secure even if the adverse receives after many copies of VK. This is simply because we assume many copy security for PRS. And so thus, This means that we can imagine authority that distributes quantum state VK to everyone. And the final remark is that there is actually non-protocol of one-time signature with quantum verification key, but with bounded number of copies of VK. And this construction is actually information theoretically secure, but the difference is that ours allow VK to be unbounded many copies of VK can be given to the antibody, whereas they only achieve bounded key security. And let me also explain some possible extension about the construction. And first, though I explained the one-bit message case, but the multi-bit message construction is trivial by just parallel running the protocol many times. And also, though I only proved one-time security, but bounded many-time secure signature with stateful signature generation is also trivial by parallel repetition, because simply we can prepare many many key pairs and use them one by one. However, we don't know how to achieve unbounded many-time security or even bounded many-time security with stateless signature generation. And in the classical setting, it is known that one-way function suffices for constructing unbounded many-time secure signatures. And one of the main techniques for that construction is that we generate a signature for verification key of one-time signature by using another instance of one-time signature. However, in our case, verification key is content, and the signature for quantum state is not we don't know how to do that. So we cannot simply use that technique. And this is why we cannot achieve, one of the reasons why we cannot achieve unbounded many-time security. And finally, let me mention concurrent work by Anand Chen Yuan, which also studied cryptography from PRS, and it was presented in the previous session in the other room today. And they constructed a commitment protocol from not necessarily length increasing PRS. And the crucial difference is that they do not assume a length increasing property unlike ours. And also they constructed what is called pseudo-random quantum path, and also they define and construct what is called PRF-like states. On the other hand, the construction of signature is unique to all. And this is a summary. So we show that one PRS implies commitment, and many copy PRS imply one-time signatures with quantum verification keys, and they can exist in the world of PQP or QMA, where one functions do not exist. Finally, let me mention several open problems. The first is to construct many-time signature from PRS, and the second is constructing PRS from one-way state generators. So as I mentioned in the construction of one-time signatures, we showed that PRS is automatically one-way, so it satisfies one-wayness. However, we don't know how to prove the other direction. In the classical setting, it is known that PRG can be constructed from any one-way function. So it is interesting open problem to do a similar construction in the quantum setting. And the final open problem is cryptography from quantum commitment. So we show that commitment can be constructed from PRS. So from this view, the quantum commitment is a weaker assumption than the existing PRS. So it is interesting to construct other cryptographic primitives starting from quantum commitment. And more generally, it is a very interesting open problem or interesting direction to study the relationship among a different kind of quantum cryptographic primitives. And so this is the end of my talk. Thank you for your attention.
Mic is not working. Any questions?
So only question to signatures means the compatibility result if the verification is classical, right? Because it's one verification giving with important the is the possibility to standard construction from the one that is the one that is classical verification.
Yeah, so what I said is that any signature scheme with classical VK can be broken by using QMA Oracle, which can solve any problem in QMA. And so this, but by the work by Bartek, PRS is there is a separation from the PRS and QMA hardness. So it is unlikely that we can construct such a classical verification key signature from PRS.
So my question is for signature with a classical verification, do you still believe one-to-one functions are necessary or no? So you can show PRS like what's your conjecture? Do you think something big in one function might be not?
Actually, I think so. That depends on the situation which you consider. So, for example, it depends on if you allow the key generation to be quantum classical and signature generation to be quantum classical. And there are many settings to consider. And in some of those settings, I think, for example, if key generation is classical, then it trivially implies one function. Oh, and but yeah, it depends on the setting.
But is there a setting where you think one function is a quantum key generation with a classical verification? Is there a setting where you believe it's not necessary?
I see. So I believe in some setting, signature doesn't immediately imply one function. So there might be a possibility that you can construct classical verification key signature from, I mean, the bigger assumptions than one function.
Okay. Let's thank the speaker again. So the next talk is an online talk.
Abanjan, do you want me to share my screen?
Yes.
Okay. Okay.
We didn't hear an introduction. Should he go ahead?
The next talk is by Omri Shmueli on semi-quantum tokenization.
Go ahead.
Okay. Okay, so this talk I want to tell you about semi-quantum token signatures. And before we talk about semi-quantum signatures, semi-quantum tokens or tokenized signatures, I want to talk about just quantum tokens. So informally, what are quantum tokens? These are quantum states that satisfy two properties. One is public verification, and the other is unclonability. And this is the baseline. Sometimes they have more properties, and now today they are a central object in quantum cryptography. So a bit more formally, what it means, what is a quantum token scheme? It's given by two efficient quantum polynomial time algorithms. The first is the generation. The generation samples a classical public key PK, together with the quantum state psi, which we're going to think of as the quantum token itself. And the second algorithm is verification. And the verification is going to get a public key and together with a state to check and going to output a bit of either rejection or acceptance for this quantum state that needs to be checked if it's legal. Okay, so how exactly does quantum token schemes come into play? You can think about a very abstract system between one sender and many receivers. All of them have quantum computers. Everything is blue, by the way, is going to be quantum entities, and everything orange is going to be classical information. So the sender is going to generate, using the generation algorithm, is going to sample this public key together with the token, is going to distribute this classical public key, and then is going to choose one of the receiver to receive this single copy of this quantum token.
Could you pause for us, please? Could you pause, Omri? We're having some technical issues.
Yeah, sure.
Oh, you have to start over. And don't start yet. Go to the first slide.
Sure. Just a moment. It's good. I'm having a warm-up. Okay.
We lost your screen share.
Ah, I see. Let's try again.
No, don't start yet.
So tell me when to share it.
Yes. Can you share the screen?
Sorry about that.
Sure, no problem. Tell me if you can see it. Just a moment. How about now?
Yes, finally, we have resolved the technical difficulties. Let's welcome again. Omri is going to talk about semi-quantum token signatures. The floor is yours, Omri.
Thanks, Pavanjan. So today I would like to talk about semi-quantum token signatures. Before we talk about these specific objects, let's talk about the most, like the baseline of this talk, which is quantum tokens. So quantum tokens are quantum states. They have two properties. They should be publicly verifiable, and they should also be unclonable. And sometimes I said this is the baseline. Most of the time they have more properties, and today these abstract object of quantum tokens, this is a central object in quantum cryptography. So a bit more formally, a quantum token scheme consists of two efficient quantum polynomial time algorithms. The first is the generation algorithm. It samples a classical public key, PK, together with a quantum state, psi PK, which we think of as the quantum token itself. This is the first algorithm. The second one is verification. It takes this classical public key and a state to check its legality, and then it outputs a bit, either rejects the state or accepts it as a legal state. So exactly how these scheme, quantum token schemes, come into play in systems, you can think about a very clean abstract system between one sender and many receivers. All of them have quantum computers, and the sender can generate, using the generation algorithm, generate a public key and a token, can take this classical public key distributed in the system, and then choose one of the receivers to get this single copy of the quantum token. Public verification is going to say that this token can be moved around in the system, and then any receiver between all of the receiver, any receiver of this token can verify this token. It can run the second algorithm, and if this state is verified, if the answer is 1, it's going to output a bit, a classical bit, together with a quantum state. So if the answer is 1, the state should be preserved, and it can be reused. And if the answer is 0, we have no guarantee what happens with this state. No cloning, which we can think of as security, is going to say that if the sender executes by the book and generates this token according to the algorithm, then sends this token to any quantum polynomial time malicious adversary, and the adversary tries to get 1 copy and output 2 copies, with at most a negligible probability, both of these copies are going to be accepted. So quantum tokens started as quantum money. This was the famous work of Wisner more than 50 years ago. They massively evolved. Also, Wisner's original scheme, it wasn't publicly verifiable, massively evolved also techniques-wise. And now we have this object called quantum tokens, which, as I said earlier, is central to the field of quantum crypto. The only concrete technique that we have for implementing these quantum tokens is based on subspace states. So these are the only quantum states that we're going to explain in a bit what they are. The only quantum states that we know are both publicly verifiable and unclonable, but they seem to have even more stronger properties. So let's start with them. So subspace states were first introduced to quantum cryptography by Amos and Cristiano. And what is a subspace state? For a subspace S, a subspace of n-bit strings, we define the subspace state of S, or just the state of S, as a uniform superposition over the subspace. Okay, so, and how do we use these states to create, to implement a quantum token scheme? This is a combination of the work of Aronson and Cristiano with the later work of Zandri. And it says that if we assume I/O, indistinguishability obfuscator for classical circuits, but secure against quantum distinguishers, we can generate a token. So the quantum part, the token itself is just going to be the subspace state. And the public key is going to be two programs, two classical programs. The first one is an obfuscation of a membership circuit for the subspace S. And the second one is again an obfuscation for the membership circuit for the subspace, the dual subspace S pair. And there is also a very elegant and efficient way to verify these states using the Hadamard transform. But it's less relevant for the sake of this talk. All we need to know is that given these two classical circuits, a quantum computer can verify these states. And in terms of security, we know that if a sender gives a quantum polynomial time adversary these two obfuscations and the subspace state, it's going to be computationally impossible, like to output two copies, such that again, both of them are going to pass verification with a non-negligible probability. Okay, so subspace states are a great implementation of quantum tokens, and a slight variation of them is coset states. So coset states are, this name was given by a later work by Coladangelo, Leo, and Zandri. And a coset state considered not only a subspace, but also two strings X and Z, two n-bit strings. And the coset state of S, X, and Z is just the quantum one-time pad of the state of S. This is exactly what's written here in black and green. The good thing about coset states is that first we need to say they can function exactly like subspace states. So we know that they can also be implemented as quantum tokens, just making minor changes to the programs, and the state becomes a coset state rather than a subspace state, and the programs become coset membership checks rather than subspace membership checks. But it has another property of direct product harness, which says that if we send these two obfuscations and the coset state to an efficient quantum adversary, it cannot, even with the most negligible probability, is going to succeed in outputting two elements, one from the primal coset and one from the dual coset. So this even which we know is at least as easy as outputting two copies of the quantum state, maybe, but it cannot even do this with more than negligible probability. And this was proved by Coladangelo, Leo, and Zandri. So why do we care about this? This direct product hardness property together with the natural properties of coset state, it gives us a very nice way to look at them as signature tokens, because they have the following two properties. The first one we call targeted sampling. So it says that for every coset state, we can define two sets. And given this coset state, we have an efficient way we can choose one of these sets and sample from one of them, like a classical element from one of these sets. And for the case of coset states, we know one technique that we define the first set as the primal coset, which is big S plus X. The second set is going to be the dual coset, which is S perp plus Z. And if we want to sample from the primal coset, we just measure this state in the computational basis and get S0 from the primal coset. And if we want to sample from the second set, which is the dual coset, we sample this coset, we measure this coset state in the Hadamard basis. The second property is one-time sampling. It's going to say that we cannot, if we have one copy, the first property says if we have one copy, we can choose one of these sets and sample from them. The second says that we never can get one copy and sample from both of them. Now, this gives this strengthening of standard quantum tokens, because what is a signature token scheme rather than just a standard quantum token scheme. It has the same algorithms for before, generation of public key and the state and the verification, but it has two more algorithms. One is a quantum algorithm that gets this token and the public key and a bit and effectively sign on this bit, 0 or 1. And the second is just a classical algorithm that verifies a signature, gets the public key and the signature and the bit and outputs rejection or acceptance. So, and again, to sign on 0, we just take this state and measure on the computational basis. We get an element in S plus X. And if we want to sign on 1, we do a Hadamard measurement and get a vector like this. Okay, and this jump, even though it might look small, from standard quantum tokens to signature tokens, gives us a major increase in functionalities. These are a few examples. There are more. And also all of these examples here, we can think of them as quantum tokens with added functionalities. We also using signature token scheme, we have all of these examples using classical communication between all receivers, but not from the sender to the receiver. So we still, this brings us to the two downsides of signature tokens. The first is quantum communication infrastructure is still necessary, at least from communication from the sender and out. And the second is that the sender can be malicious, as can generate a faulty state. So if the sender behaves honestly and just generates this token and send this to the receiver, the sender can be malicious, generate this public key honestly, and then just send garbage instead of the quantum token. And which brings us to the motivation for semi-quantum tokens. So what are semi-quantum tokens? They started as semi-quantum money, an idea by Radian and Satat. And now we have generalized them to just be semi-quantum tokens. And what are these quantum token schemes? They are regular quantum token schemes, but the sender can be classical. And the key technical adding is that we have classical delegation of token generation. So before, if we needed to generate a token, the sender is quantum, it generates the token by itself, and then it sends it to one of the receivers. Now the sender is a classical algorithm, going to interact with one of the receivers. And after interaction, the receiver, if it behaved honestly, is going to hold this quantum token, and the sender holds the public key, and it can distribute it in the system. Security for semi-quantum token schemes says that if the sender interacts with the efficient quantum adversary, and after the interaction, the adversary wants to output 2 copies, again, like before, with the most negligible probability, both of these copies are going to be accepted. But the point here is that this adversary is going to be the one to actually generate the state. And still in semi-quantum token schemes, this state is unclonable even for the generating computer. So the computer sees the classical instructions that the sender sends, and it still cannot produce more than a single copy. Okay, what we know in terms of constructing semi-quantum token schemes, we have one protocol by S2021 that says that if we assume the quantum sub-exponential hardness of LWE, and also quantum secure I/O for classical circuits, then we can construct a semi-quantum token scheme. More precisely, what the previous work shows is that this generated token is a coset state also. And the public key is exactly the same like before. These are obfuscations of these membership circuits for the 2 cosets, primal and dual. The good side is that the previous work shows that this state is unclonable. The bad side is that we actually later got to know that while this, if this receiver is malicious, it cannot clone the state, it can still output 2 elements, one from the primal coset and one from the dual coset. So to recap, we know that fully quantum coset state, when the generator is trusted, have this direct product hardness property, which in more effectively, it means that if I send you the quantum state prepared and you try to break direct product hardness, you can't. However, if we are interacting and I give you classical instruction for generating the state, which is exactly what this says, you in fact can generate two elements, one in the primal coset, one in the dual coset. So we don't have direct product hardness for semi-quantum coset states, but we do have for fully quantum coset. And now our techniques. So we show that we can do targeted sampling and also show that this sampling is one time for semi-quantum coset states. So let's also remember what exactly is targeted sampling and one-time sampling. But before we do that, let's start with a protocol that already exists, which is of S2021. This is the protocol for delegating the generation of the coset state, and it doesn't really import it. It's not so important that we know what's happening in all of this. Mainly the first message is important. And what is the first message? This classical sender is going to sample a classical random subspace of n half dimensions. And then it's going to encrypt the classical encryption, the classical description of the subspace using classical QFH, like a classical encryption of quantum fully homomorphic encryption. It's going to send this QFH encryption to the receiver, and then the receiver is going to generate the state by itself. And the point that we care about is that because for the receiver, the S is hidden. It generates the coset state of S, but it doesn't see S. So from the security of the QFH, it should be computationally hard to find any non-trivial vector inside S. More elaborately, what the security reduction says, it shows that if a malicious receiver clones this quantum state, it outputs two copies of the coset state, you can derive a non-trivial vector inside S. And now we want to prove for this protocol, change it somehow. So we have targeted sampling and one-time sampling. So let's recall what it means. Targeted sampling means we have two sets that we can choose from, and every coset state can give you a sample from one of them. And one-time sampling means that this sample is one time. It's at most one sample from each coset state. And we know that we don't have, we cannot choose the two sets for our semi-quantum coset state cannot be the primal and the dual cosets. So here is what we're going to do. We're going to use, instead of looking at the primal and dual subspaces, we're going to look on two parallel cosets that join to S plus X. Specifically, define S0 as a subspace of S, which has one less dimensions, and another vector which is inside S but outside S0. And the two halves of S plus X are going to be, the first half is set one is going to be S0 plus X. This is a coset. And the second coset is S0 plus W plus X. Okay, so this is our choice. Until now, we didn't prove anything for targeted sampling. And in the paper, we show a quantum algorithm, a polynomial time quantum algorithm that given the following. It doesn't get only membership programs for S plus X and S pair plus Z. It gets S0 plus X and S0 plus W plus X. So for the two halves of the coset S plus X, and also for the dual coset, and a bit to sign and the coset state. And it can project this coset state onto this coset state with almost probability 1. Okay, when we know that if we measure this coset state, now we're going to get our wanted element from the chosen set with probability 1, given the fact that we already have the state. And the only change we need to make to the protocol is that in the third message, the sender needs to change to send all three obfuscations rather than only two. Good, so we seem to have targeted sampling. What about one-time sampling? And this translates to the question, is it hard to compute for a malicious receiver in the protocol that we just saw? Is it hard to compute two elements, one from set 1 and one from set 2? Let's start with a warm-up for the security. So the warm-up is going to say that the receiver is going to try to find these two elements given only the first message. And this would also, of course, be hard because it gets only less information. And what one can verify that if we have these two elements, one from S0 plus X and small s1 is inside S0 plus W plus X, then this U0 and this V0 are inside S0. The X's cancel out and we get a vector, this sum from the closure in the subspace S0. This is a vector inside S0, and this is a vector W is in S but outside S0, which means that this sum, which is this sum, is inside S, but not S0. And we know that S0 is in particular a subspace. It contains the zero vector, which means that if this sum is inside S and outside S0, it's particular a non-trivial vector inside S. Which means that this is already computationally hard, which is good. It is hard for a quantum polynomial time receiver to get one message and output these two elements. But the real security game is given all of the protocol and then outputting these two elements. So crucially, it's also given the third message from the classical sender to the receiver. And this should be still computationally hard. So let's see what happens. Usually our main technical tool for showing indistinguishability in this realm of unclonable cryptography, quantum tokens, is the main technical lemma of Zandri 2018. This is also called the subspace hiding property of obfuscation, or just subspace hiding obfuscation. It says that if we assume quantum secure indistinguishability obfuscation for classical circuits and assume post-quantum injective one-way functions, then for every subspace of n-bit strings, this subspace can be fixed. And the dimension of the subspace is half the dimensions, like n-half. These two distributions are going to be computationally indistinguishable for quantum distinguishing. So the first one is just taking the membership circuit, the classical circuit that checks membership in S, obfuscating it, and sending the obfuscations. This is distribution number one. Distribution number two is first sampling a super space of S. So a random subspace T of 3/4 of n dimensions, conditional containing S. So much larger subspace that contains S, and then obfuscating the membership circuit of the subspace. Okay, and then sending these obfuscations. So obfuscating just S and obfuscating random superspace of S are going to be indistinguishable under assuming IO and post-quantum one-way functions.
Maybe you should wrap it up.
Yes, 2 minutes.
Can you wrap it up soon?
Yeah, sure. So we can try to use this, main technical lemma to switch from this distribution to this distribution. And the point is that we don't know how to do it. There are a few reasons why we don't know how to do it, but the main one, because I don't have time to explain, but this last bullet is the most important. We don't know how to prove that an adversary that is going to output these two elements is going to necessarily avoid the dual subspace of T1. Okay, we want to output a vector inside S, but now not only S, which is non-zero, S and should be not in T1 pair, which is one of these big subspaces. And to wrap it up, our main technical lemma shows the following. Under the same computational assumptions, and if we have any fixed S of the same dimensions, it is impossible to get a sample from the T distribution, like getting an obfuscation of the membership check for a random big subspace T, conditional containing S. And it's going to be impossible to do two things together. You cannot hit the dual of T with a noticeable probability, but not hit the background, which is S perp, with a negligible probability. Okay, this is the anti-concentration lemma. You cannot concentrate in the dual subspace of T, where you get an obfuscation of T. And yeah, that's it. Thank you.
Okay. We won't have time for questions, but let's thank the speaker again.